So today we are very happy to have Emil Bergholz here to talk about non-Hermitian topological physics. And Emil, since 19, he is a full professor and Wallenberg Academy Scholar here at Stockholm University. And before that, he's had a postdoc career in Germany, first in Max Planck Institute at Dresden, where he ended up as a group leader, and later he was Eminöter group leader at Freie Universität in Berlin. Before that, also, you might think that to give a colloquium here, you have to come from some other place. But, Emil is a proof that if you are sufficiently distinguished, you can give a colloquium talk here in Stockholm, even though you are from one of the institutes here. And Emil will talk about non-Hermitian topological physics, and that's a subject where he and his group has been very important, actually, been initiating lots of the work. And earlier he worked on other aspects of topological physics, Schoen installators, quantum Hall effect, etc. So, Emil.
Thanks a lot, Hans. And I'm happy to see such a good air quality in here. I'm checking it, actually. Thanks, Hans, and thanks for the committee to invite me to give this talk. The topic is this one. It has one familiar part to many of you, and one that seems a bit provocative, right, the first part. And this is sort of a leap of faith we did 4.5 years ago, jumping into this field. And we did it first with Jan Budisch, who was a postdoc here years ago, and now is a professor in Dresden, and Flore Kunst, who was my PhD student. And also later many people joined our pursuit, and in particular I would mention Elisabeth Edvardsson, who's soon defending her PhD thesis, Marcus, who defended in the spring, or in June, and Yuan and Kang, who were postdocs in my group and have now moved on. Yuan is still here, though. The reactions we got 4.5 years ago were, are you really serious? Have you totally lost your mind? We're working on quantum physics, quantum many-body physics, and people are thinking this is sort of heresy. You work with Hermitian systems, this is our fundamental description of the world, and I mean, that's correct. If we have non-Hermitian systems, we immediately get complex energies, non-unitary time evolution. It's like opening a Pandora's box. Oops, wrong direction. And that's true, it is really opening a Pandora's box. But it's everywhere, so we better open this Pandora's box. We don't really have a choice to keep it closed if we want to describe the reality we are living in. Think about friction, resistivity, dissipation. It's really everywhere. Remember your first courses on mechanics, right? You have friction all the time, and then you get sophisticated enough to learn about Hamiltonian mechanics, and then suddenly you sort of throw away friction. You forget about it, pretty much. Then you learn quantum mechanics, and you still don't reintroduce friction, right? But I suggest that you should. In particular, this has been popular for a long time in photonic systems, where you have either gain or loss. So you have some light, photons, that are either sort of disappearing from your system of interest, or you can actually pump them to get more. Classical metamaterials, I will show you examples. This is a very key concept. You know from your first class in mechanics that you have friction and such things. And had you not learned these more advanced courses, you would have thought that this is totally normal. And yes, it is normal. It's everywhere. Also, you can look at open quantum systems. And one of the most famous, if not the most famous nowadays, equation from Stockholm is the Lindblad equation. It describes the time evolution of density matrices of reduced systems. And there you have a Liouvillean, which takes the role sort of a Hamiltonian. And the key thing here is that the Liouvillean isn't, in general, Hermitian. Nevertheless, it's a perfectly valid quantum mechanical description. Many times people talk about effective non-Hermitian Hamiltonians, and they work in certain cases, in certain limits, and so on. But the more fundamental statement is that the Liouvillean is not Hermitian. And you need to understand the physics of non-Hermitian matrices. It's also an effective description of systems with finite lifetime states. And we're all deadly, right? We know that there's a finite lifetime for us. The same goes for quasi-particles in solids, and so on. And in particular, you can think about the imaginary part of the energy, which is sort of the eigenvalue of the non-Hermitian Hamiltonian, as inverse lifetime. It goes to zero only in very specific cases. You can think about scattering problems, resonances, and so on. So in a way, already from the start of quantum mechanics, basically, non-Hermitian phenomena have been implicit. They've just not been highlighted. It's sort of swept under the rug. So you can look in old papers by Feshbach, by Majorana, and others. They talk about actually non-Hermitian physics. Oops. Now I need to go through this again. So the thing that's new, and that's been going on for the last 4 or 5 years or so, is the perspective of topological phases, and how that, which is a well-developed field, relates to uniquely non-Hermitian phenomena. So something about topological physics first to set the stage. We have the bulk boundary correspondence, which is really essential for topological physics. It dictates that we have a bulk topological invariant calculated in geometries with periodic boundary conditions, such as a torus, etc., like a periodic Brillouin zone. And that relates to predicted boundary states that cannot disappear unless you change this integer, which is, as Hans famously described 6 years ago, as different types of bagels or donuts or pretzels and buns and so on. The topology is robust even if you take a rather big bite, unless the bite is so big that you actually puncture this. When you change the number of holes, you change the genus, you change the topological properties. And via this bulk boundary correspondence, that means that you have to take a big bite to change the boundary states. And the boundary states relate to conductance properties of solids. So there are 2 keys that underpins this and that are often forgotten. The first one, and I will come back to this several times, is the stability of spectra. So what goes on here is really that when you open up, take a torus, and you cut it to get a cylinder, then the torus should tell you about edge states on the cylinder, boundary states on the cylinder. That means that you cannot have a complete rearrangement of states. So you need to have stability of spectra. The other thing is that we need to know how phase transitions occur and how low energy levels cross. That is, what happens when we take a bite so big that the donut collapses. So the famous example of this that started the entire field now 40 years ago, or over 40 years ago, is the quantum Hall physics. And I'm sure you have seen this many times. But the remarkable thing here is that you have a big mesoscopic sample that you make conductance measurements on. So here is resistivity. And it takes perfectly quantized jumps. And the value of these plateaus is quantized in integer units of h over e squared, h squared. This is remarkable for being a property of a dirty sample. And that is why, so to explain this quantization, it turned out that Thouless and others came up with this topological explanation. There's really An invariant, that's an integer that cannot be changed in small pieces. It changes in finite steps. And nowadays, related ideas are all over theoretical physics. So you've heard perhaps about holographic principle, how boundaries tell you things about the bulk. And in particular, this is popular both in high energy physics, all of their correspondences, and in entanglement. So you have these area laws of entanglement. The entanglement lives on the boundary, but it really describes via the holographic principle really the essence of the bulk as well. And there is much more than quantum Hall in materials, actually. There are now, if you take into account symmetries, you can form periodic tables. So here you have different symmetry classes, and here you have different dimensions, and quantum Hall is just one of these. There's a whole zoo of things. If you take more and more symmetries into account, you can make bigger and bigger and bigger tables. There are now tables taking into account spatial symmetries, which have thousands of entries. It's obvious when you know it's there, but before you knew it was there, you didn't know what to look for. There are also topological semimetals, like graphene and Dirac and Weil semimetals, that have certain topological properties, and they are not contained in this table. These are only insulators. And there are also classical analogs. This really kicked off in photonics and was pioneered by Haldane, who got the Nobel Prize for something completely different. But he pointed out that Maxwell's equations can essentially be Chern insulators or quantum Hall systems. They can have protected chiral edge states. And in mechanical systems, this was starting to be discussed in around 2015. And here is an experiment that I want to show you what's going on. It's from Sebastian Huber at ETH in Zurich that have made really beautiful examples. So these are really mechanical things. These are like springs and big things that you can actually touch. So let's see if the movie starts, I hope. Yes, now it will. And at some point you should see something starting to occur here. They send in a wave package. Yes, and they highlight it even. And it's supposedly going around the system at the boundary. And this is a leaky system a little bit. You see a bit of movement inside, but it basically restricts itself to the boundary. And this is a topological insulator made out of a mechanical material. But of course, we know from our first course in mechanics that in mechanical systems there are effects like friction, etc. So that's what we'll come back to. But all of this, the entire field of topological systems, is based on the classification and analysis of Hermitian matrices. So what if we do a similar analysis of non-Hermitian matrices and leave these kind of typical physics approximations away? So I found this sticker very nice, the spherical cow approximation, and it only works in vacuum. That's a bit provocative, right? And I'll hit a bit on the non-Hermitian case as well later on, so it evens out. So I'll give you 3 answers to this question. And this is the first one. The first answer is that uniform non-hermeticity makes everything broaden, everything fades away. That's the typical expectation. So it's sort of considered as bad. People that do topological physics do everything to protect it from dissipation, because it kills the thing you're looking for. Well, you can look for something else, but we'll come there. Here's one book that I appreciated a lot as a student. It wasn't in our course material, but I bought it anyway, by Matuk. And he pointed out that a real particle, sort of outside of a material, is different from a quasi-particle in terms of inside a solid. And he pictured this like a horse, like this. And this is a quasi-horse. It sort of dims out. You don't really see what it is. It's very pictorial, but there is something to it. And this would be sort of that sad story of non-hermeticity, that it sort of fades things away. Here's the second answer. Actually, non-unitary time evolution, which comes from non-Hermitian Hamiltonians, is needed to prepare interesting states, like ground state cooling. Think about the system, and you want to do an interesting experiment. You need to get it there. If you have unitary time evolution, you're not going to change the energy of the system. It needs to evaporate some energy, right? So it's implicitly there, but since we typically think about, okay, we have an interesting state prepared, let's analyze that, but the way there is really a non-Hermitian way, or non-unitary at least. We're actually doing something with Walid and Yuan and in Mohammed's lab at the moment, where we're sending in light, and we're building a non-Hermitian waveguide array, such that it actually targets the interesting states regardless of what we send in. Well, there is some fine-tuning and some fiddling around, but you can do this. You can prepare such that you get states at corners, at edges, and in various configurations. I'm not going to tell you any details because this is not published. I hope it will be out very soon. Right, guys? And then there's the third answer. And that's that generic structured non-hermeticity really changes everything. This is really the Pandora's box. It opens new worlds. It challenges the basics of stuff that we learn. So what about the stability of non-Hermitian spectra? One of the basic properties that I mentioned. Another one, how do energy levels cross? What about the bulk boundary correspondence? And if we've gone through these basic questions, we might also dare to ask whether this can be useful or not. So let's find out. Using this sort of toy, as we think of Hamiltonians that are no longer Hermitian, and if you want, you can say that this is really a cylindrical cow, if the Hermitian one was a spherical cow. It's not going to be in every case accurate or realistic or anything, but the generic thing is there. So if we look at very generic principles, properties of matrices, this is the analysis we need to make. Whether we call them H or L or whatever, is not really the key point. So stability of non-Hermitian spectra, our first question. I'm going to make some strong claims here. The first one we're used to, and I don't think you react to this one, and that's that stability of Hermitian eigenvalues. So shift in eigenvalue E are bounded by the largest eigenvalue of the perturbation. And that's in particular if the eigenvalue of the perturbation hits an eigenstate, then you get this shift that saturates this inequality. And most other states are, of course, typically changed much less. Non-Hermitian matrices, non-Hermitian n by n matrix, we have instead this relation, that the shift in energy is bounded by some constant of order 1 times the nth root of the perturbation. And now it's the norm because the perturbation doesn't need to be necessarily normalized, but just think about it as 1 times the nth root. Why is this spectacular? It looks very innocent. But already for n equal 2, already for 2 by 2 matrices, we can learn something fundamental. It's going to be square roots, non-analytical. For a small perturbation, the square root of the small number is much, much bigger than the number itself. And if we go to n tends to infinity, we have an order of 1 change for infinitely small epsilon. And here it is. Here is such a block, and with a perturbation epsilon. It's a so-called Jordan block that we perturb. So let's do the calculation. That's also the great thing about breaking into a new field, that you can do remarkably simple things that are still kind of new. So let's look at the characteristic polynomial, so the determinant of this Hamiltonian minus E times unit matrix. So now we calculate this determinant. We get minus e times minus e times minus e n times. Okay, that's all we get there. We get zeros, and then we get epsilon times all of these ones, n minus 1, n ones. And that should equal 0. So that means that we get minus e to the power n plus epsilon equals 0. And we see that all eigenvalues e are, well, it's some root of unity times the nth root of epsilon. And that was my claim. Here is the example that saturates this inequality. And note also that not only one eigenvalue changed, but all of them changed dramatically at the same time. So now think about a very large matrix and add a tiny epsilon. If it's infinitely large, essentially, you get order 1 change in all eigenvalues. Next question. How do energy levels cross? And this will be sort of a story about n equal 2, because this is very important, special case. And it turns out to already be interesting and abundant. So this is supposed to be interesting, and this is supposed to be abundant. I will tell you precisely why. We take a minimal example. And now you know how to diagonalize matrices like this. And just to make you think yourself, I wrote alpha instead, and alpha can be big now, big or small, and I switched the order of it, just to make you think. So eigenvalues, plus minus square root of alpha, obviously. And if you forgot about the square root, you might use Wikipedia. And if you look at Wikipedia, you will find this Riemann sheet description of the complex square root. And you realize two things, that you have to wind twice to get back to the same eigenvalue. And that means that we have some sort of half integer winding number associated with this, if you wind around the origin. And we have a branch point at the center, and we have a branch cut somewhere. And you necessarily have these. These are topological properties, which has physical consequences that we'll come back to. If you do a little bit more work and look at the eigenvectors, I'm not normalizing them on purpose, but look at the right one with plus and minus. It looks like this. And you see that for plus and minus are not orthogonal unless alpha is 1, essentially. And you also have left eigenvectors. That's something you tend to forget when you start doing quantum mechanics, right? Because left and right eigenvectors are the same. Here, they are not the same. They are different. Now, we use this general result and plug in alpha equal to 0. Then we have what's called an exceptional point. And it's exceptionally interesting, not exceptional in very rare. Then we have only one eigenvalue, so 0. But we also only have one right eigenstate and one left eigenstate. So both eigenvectors and eigenvalues coalesce. And left and right states are essentially opposite. You see that the right one has the second component finite, and the left one has the first component finite. This has been known for a very long time, at least since Kato discussed it in his book on perturbation theory from, I think, the 50s or so. And Michael Berry sort of brought it up to more modern language in this nice paper, in a very obscure journal from 2004. So the question is this relevant for physics? And of course, I wouldn't be here telling you about this if it wasn't relevant at all for physics. So yes, exceptional points have a long history, especially in optics and photonics. In fact, I remember hearing about them from Michael Berry himself when I was a student here, quite many years ago now. And recently there was this review in Science about exceptional points in optics and photonics from 2019. right? So they really exist. They have lots of physical applications. But isn't it fine-tuning? You need to go close to such a point. Most matrices won't look like the one I wrote down, right? So if you're really against math, you can relax for a little bit. But there are some things that I'm sure that each one of you could follow if you sit down with paper and pen and work out. And that's why I'm going to do these small calculations also. And I will notify you when you can sort of, yeah. So the first step here is to ask, well, when can we expect two energy bands to cross in Hermitian systems? This is a very old question. Sometimes credit is given to Herring in 37. Sometimes Wigner and von Neumann from 29 get the credit. And even though I understand German, I couldn't find it in their paper. So I give credit to Herring where I know it's actually there. So write a generic 2x2 Hamiltonian, which depends on some momenta, so a Bloch Hamiltonian. You can decompose it like this in terms of the three Pauli matrices. So you have a vector D, which is real valued, times the sigma matrices, plus a constant. And the constant will be irrelevant, so we can forget about it. And this is something I always give to the bachelor student as either on the exam or as homework to figure out the eigenvalues of such a matrix. And the trick is just to square this and use the Pauli matrix algebra. And you find that the eigenvalues are plus minus square root of the length of this vector D, so the first component squared plus second component squared plus third component squared, plus a constant, which we're not interested in because we look at band crossings. So we need this to be 0 under the square root, plus minus 0, so we get the same. So there are three equations. Hence, we will need tuning 3 parameters to generically find the solution. Right? And you can, if you were in 2D, you would be very lucky to find the solution because you have only 2 parameters per 3 equations. And that's what happens in graphene. And the reason it happens in graphene is that you have PT symmetry. So if you think about PT symmetry as complex conjugation, basically, you can throw out the sigma y Pauli matrix because that's complex. And in 3D instead, it's stable and generic. So if you find a solution, any perturbation might move that solution, but it's still going to be there. So the simplest example of this is the Weil Hamiltonian from Weil in 29, sort of motivated by beauty. And then after a while, people thought, oh, maybe the Weil Hamiltonian describes neutrinos, but once it was found that neutrinos have a small mass, this was sort of out of the window. However, these things occur in solids. So while semimetals were discovered around 2015, and for instance, this is one of several papers that came at the same time, and they show, in particular, these arcs at the surface of the system. An arc is something that doesn't close as it should, as you would expect from a periodic system. And you can think about this as some sort of vestige from the Dirac strings of these Weil particles. Oops, wrong direction. Now we go back to the non-Hermitian case. So we saw that in Hermitian system we need to tune 3 parameters. How about non-Hermitian ones? Well, we start with a similar model, but now we throw away the constant part. But since it's non-Hermitian, the D vector can be complex. So square and take square root, and then we get the length of the real part squared minus from the I squared, the I squared, imaginary part, plus 2 times the scalar product between these things. And here really comes the miracle that having 0 energy really means 2 real equations. This one is 0, and this one is 0. If we put the imaginary part to 0, this would die immediately, but this single equation would then be 3 equations because each component would have to vanish. So extending your space, making a more generic Hamiltonian, actually reduced the number of parameters you need. And one can show that every solution for this, which doesn't have a 0 d vector, is exceptional. And you can see that by just choosing a basis and do a one-line calculation that I leave for you. You can see the slides or the YouTube movie later if you want to go through this. It's really quite instructive. But the bottom line is here, exceptional points are much more abundant than degeneracies in the Hermitian case. So I would say that in Hermitian normal topological systems, that insulators are the most interesting. It turns out that the gapless systems are more interesting in the non-Hermitian case. So if we look at the spectrum, we just take a non-Hermitian tight binding model, a random one, and look at some part of the spectrum, we will find that the exceptional points are non-analytical. That we already knew from the square root. But let's just plot such a thing near one of the square roots. This looks very sharp, right? It feels like if you would put your finger there, it looks like you would hurt yourself. Get the needle in your finger, right? And if I would plot an ordinary linear crossing, it wouldn't look that sharp. And also, if we now look at real parts and imaginary parts, in something which has 2 of these, you would find branch cuts connecting the points, and both in the imaginary and in the real part. So we can have a closer look at this. And this is again something you could sit down and follow. So if you just stare at this expression, as Johan did a couple of years ago, you will find that you divide space into 2 distinct parts, one where this thing is larger than 0 and one where it's smaller than 0. And you do the same for this quantity. Both are real. You see that the exceptional points sit here at the intersections, because then you have square root of really 0. 0 here and 0 here. And you also see that you have real part of energy being 0 whenever this is 0, so on this line, and this being negative, which means on this line. This was on this line, and this should be negative, so it's inside here. So we can color this by red, and we find that's the arc. That's where we have real part of energy 0. And that's irremovable. That's this branch cut that I talked about in the minimal example. You will always get it. And similarly for the imaginary part, you can work it out. So these are really protected by this half winding number that you need to wind twice to get back to the same energy eigenvalue. And these are experimentally observed. This looks a bit similar to this Fermi arc you saw on the surface of a wild semimetal. So here there is experiments and simulation of non-Hermitian models. And you sweep in frequency, which is sort of the energy, or real part of the energy. And you go from high frequency to lower and lower. And here is where you're supposed to see the arc. And yeah, experiments look almost better than theory, but it's sort of a matter of taste. There's of course some imperfections in every experiment and some limitations in all the modeling. But this is really a band structure that you wouldn't see in a normal Hermitian, non-interacting, I should say, system. You could also imagine getting similar things from disordered interactions in ordinary 2D quantum systems. If you go to 3D, which we did, you find very cool stuff if you're mathematically minded. You find that you get, instead of points, you get lines. That's the natural thing when you extend one dimension higher. And you get that these exceptional points can form lines that are knotted. And the Fermi surface that corresponds to that turns out to be the Seifert surface of the knot. So old maths of knot theory suddenly pop up in a physically motivated context. And I found this very cool because 2 notions of topology are combined. Hermitian generic line-light nodes occur in 4 dimensions, but of course in dimensions larger than 3, all knots are trivial. But in 3 dimensions they are not. They are generic. You can't remove them if you have them there. unless you sort of contract them to a point and annihilate the gaps. Question was, is this physically meaningful? And of course we wrote in our paper that it's physically meaningful, and I'm not sure that we really believe that it would be physically meaningful. But to our surprise, very quickly afterwards there were experiments. First, looking at exceptional rings. That has also been suggested by other people earlier, with rings in optical systems with waveguides. But more importantly for us, you find exceptional knots and Seifert surface in some interferometric experiments. I should say that these are really more like simulation of some theory rather than looking at the solid that you want to describe. It's very much engineered experiments. It's like running the theory on a physical thing. Nevertheless, I find it very cool to have abstract things like Seifert surfaces and knots coming out in experiments. And you can even do much more complicated knots than the ones I showed you. I showed you the simplest example. And there is much more. Talking about complicated stuff, you can classify this stuff, as Marcus has been helping me to work out. Also in terms of symmetry and topology. There are new notions of gaps, topological phases. You can have so-called point gaps or line gaps. And line gaps is more similar to what we have in Hermitian systems. It was studied, for instance, in this paper by Kawabata et al. And there's a novel bulk boundary correspondence that I will come back to. An ample of experimental platforms. And here is our review in Reviews of Modern Physics, where we try to describe this at the best of our knowledge, end 2019, start 2020. And well, there is still some inflationary period of the field, so it's getting more and more and more. And I guess this was basically the latest time at which one could write a comprehensible review article of the field. But it's a good place to start, I hope, still. But some more practically minded people are not happy with seeing knot theory in some engineered experiment, but ask instead, can we use this for anything? So I'll shift gears and discuss prospects of actually using this. One thing that came up as a more or less obvious idea was use exceptional points as sensors. The theoretical proposal was in 2014 already, in the sort of optics and microcavity community. And soon enough, experiments followed. So this was a PRL, and then there were 2 Nature papers with experiments. And you can see here, here's the dull Hermitian degeneracy. And if you make a small perturbation, you won't change the energy very much, or the signal. But if you have this very sharp thing, which is similar to what I showed you, then you have a huge amplification of a small signal. And that's what these papers claim to measure with these optical ring resonators. And people who want to measure weak signals, of course, became very happy and published things in journals called Physics of the Dark Universe, for instance, probing dark universe with exceptional points. And you see here, this looks like axion coupling or something like this, and square root of that small number would be much bigger, or third root even would be even better. Great. But these sensors were not a revolution. And you might ask why. Why can't you now, if you were close to measuring a number, then you should easily measure the third root or even square root. Actually, it turns out to be quite complicated. And bad news are published, for instance, in PRA, and the year after. No exceptional precision of exceptional point sensors. Very bad news. The story is quite easy to see. The measured signal is actually depending also on the eigenstates, and the eigenstates necessarily change dramatically away from the exceptional point. if you remember my 2 by 2 example, we have the square root of alpha in the energy, but we also had the square root of alpha in the eigenstates. Or if we call them epsilon, if they should be small, he calculated a signal in a very pedagogical way and found a square root from eigenvalue and square root from eigenstate. And we end up with linear, which is exactly what you expect for a Hermitian sensor, so no gain. But people like exceptional points, so they strike back and point out, in a very nice paper again, that if you do more general measurements, you might be able to have a fundamental advantage. So good, this is not killed, but it's starting to look quite complicated. And when things look complicated, you look for advice. And well, we didn't talk to Frank about this, we talked about it later, but this is a quote I like more and more. And in particular from here, when things look complicated, that is often a sign that there is a better way to do it. So that's what we're going to try to do. We have a wish list. What would be good to have for a sensor? Well, single isolated mode, such that eigenstates don't change immediately. Large n, why is that with n equals 2 and 3? Why not a few hundred? Operational at many large orders of magnitude, if possible. No fine-tuning. When we go to higher and higher order exceptional points, you obviously need to tune more and more parameters to get all of the eigenstates and eigenvectors to coalesce. It turns out to be only order of n instead of order of n squared, as for Hermitian matrices, but it's still too much. We would like to have topological robustness, possible to realize with existing building blocks and practically useful. So we'll see how far we get. I can't promise you we get all the way. We won't kill the field yet. So large n, that's something that's been essentially untouched because people in optics communities and so on like to have small matrices to deal with. Unlike condensed matter people that like to have huge matrices, we don't like to, we just get stuck there. But there was an early exception by Hatano and Nelson. We had a PRL in 1996. But that was, on the other hand, a bit before the time of topological insulators, so all the same connections were not made. But they looked at a very simple and nice model that you have some amplitude JR to jump to the right and another amplitude to jump to the left in a lattice model. And if you have n sites, you have an n by n non-Hermitian Hamiltonian. In particular, if you turn one of these off, you would get the matrix that I showed you, the n by n matrix that I showed you in the beginning. And if you would connect the ends, you would get the strong signal that I talked about. But that was not really known at that time. So when we jumped into this field, we realized that there was this open problem of the bulk boundary correspondence in non-Hermitian systems. And we gave our contribution to this in 2018. And there's another one I should acknowledge, also from 2018. In fact, that was on the archive a little bit earlier than us, even though we were published earlier. So the thing here is that if you have a model which has a spectrum on periodic boundary conditions which is gapless, for instance, as in this extreme case, then you cut it open, then you can rearrange the entire spectrum, and in this case it becomes a spectrum of a Chern insulator on a cylinder. It has a chiral edge state and it has bulk bands. So these offer some insights into what's going on. And I could tell you in private what's going on in detail, but I won't have time here. But the nice thing was that about a year and a half or a little less, there was really an avalanche of experiments showing these type of effects. Here in topological circuits, so it's essentially electrical circuits, mechanical or robotical, as they call them, systems, and in quantum walks, that's again optics systems. And then lots of other things followed. I'm just posting here, they were published all in very high profile journals, but I post the archive numbers to show you that these were just within days, essentially. And since then, the interest has grown a lot. So our suggestion, that was something that Jan and I thought about. What if we consider a non-Hermitian SSH chain with an odd number of sites. Typically, when you look at this, you always have an even number of sites for topological reasons, for Hermitian topological reasons. But the nice thing about this is that you have pinned at 0, you have one isolated state. So if you look in the region here, for instance, as we will do, we're in the region here, this is a function of one of the parameters of the model. You see that you have an isolated mode. And that isolated mode corresponds to a right eigenstate and a left eigenstate, both of which you can calculate exactly with no effort, essentially. I'm just posting it here. I'm not going to tell you about it, except the one thing that they are different. They're not the same as they would be in the Hermitian case. So now let's couple the ends of this chain. So essentially we want something coupling the first and the last site. So in practice we have to curl it up such that we get a matrix element between the end sites. And we could change this, for instance, by changing the medium between the sites. And we calculate the shift in the energy. And it turns out that to calculate the energy in perturbation theory, you can do this because it's a single mode. You need to use both the right and the left states. And you can calculate this as just geometric series. It's a very simple calculation. It turns out to be exponential in the large system limit. And this is also true in the Hermitian case. But in the Hermitian case, alpha is always negative. So it's exponentially bad sensing thing. But this alpha can be positive in a non-Hermitian case in a finite parameter region. And I'll try to provide some intuition why this can be positive and large. So the intuition here is that case 1, that's if left and right eigenstates are both at the same boundary. And that's always the case in the Hermitian case when left and right are really the same state. So then we have this situation. Both live at the same. Now I put them on the left side. They could both be at the right. It doesn't matter. So then you calculate the coupling, the perturbation, which was the coupling between the different ends, between the left and the right. But they are at the same end. So this coupling will only give an exponentially small matrix element. Whereas the overlap between the two states is of order 1. They're localized at the same side. That means that if you plug it into the formula for the shift, it's exponentially small. That's very bad. That's not a good sensor. That's the worst sensor we could ever think of. The other case is if left and right eigenstates are at opposite boundaries or ends of the chain. The boundary of 1D system is an end. So we have, let's say, left on the left side and right on the right side. It can be the opposite as well. Left and right has a different meaning. Then this matrix element for coupling is of order 1 times the coupling strength. But the overlap between left and right is exponentially small because each one of these states are exponentially localized to opposite ends. Hence, we get an exponential shift in eigenvalue. So here's a numerical check. You can do a numerical experiment on this. And I plot solid lines, that's the perturbative results. And dots are exact numerical results. So let's look at this black line. So here we have taken a perturbation of 10 to the minus 14. That's as much as our laptop manages, basically, to be accurate. So couple them with a strength 10 to the minus 14. And then you look at the shift in energy as a function of the system size. And then you see that these lie perfectly on the perturbative analytical result until they level off and saturate. And what's happening here? Well, you get to the range of the energy gap. So the SSH model has a finite energy gap, and when you're at that order, the perturbation theory won't work, so it won't continue forever as the perturbative result does. But these are many orders of magnitude. You see 10 to the minus 14 up to at least 10 to the minus 2. So there's 12 orders of magnitude, something we really wanted. If we would like to have an even better sensor, we would have to have a better computer to check it. And of course we can, but we thought this was good enough. And also a couple of hundred sites, you might, for other practical reasons, not want to go much beyond that. Then the question about topology, is this topological or just some coincidence? That it was valid in a finite region, that's promising. And it's even more promising when you look at this order, and it works very nicely. But let me get to the topology of it. There's a winding number of energies in the complex plane. And this is an invariant that would surprise those of you who know about topological physics, because in topological physics, Hermitian physics, we have winding of Bloch states in a Brillouin zone. Here we have winding of complex energies. And moreover, the ones for 1D that are winding of Bloch states, they are depending on the so-called chiral symmetry, so they are very fragile in 1D. Here they are not depending on symmetries. So this is something which has the status of a Chern number, essentially, in the Hermitian case. You can add whatever disorder you want, break any symmetries, as long as it's small enough, it won't kill the qualitative features. So what did we actually get? Well, we got a linear shift, but with an exponentially large prefactor, rather than the nth root. So here is this stable effect with no fine-tuning that we find in our type of sensor. Linear, but exponentially amplified. This is the exceptional point, which has this fine-tuning thing. And if you have a finite resolution limit, these are essentially equivalent. But this one has the problem that the eigenstates necessarily change in the same dramatic way. Here, eigenstate stays essentially unchanged until you hit the level of the gap. So first order non-degenerate perturbation theory worked, therefore there is no significant change in the eigenstate. Just think about how perturbation theory looks. First order shift in energy just uses the unperturbed states. So if that works well, it means that unperturbed states are good. There's a single isolated mode, hence the signal is also exponential in system size. There is no extra factor that kills this energy factor as it was in the exceptional point case. So one can do that calculation as well. So then, to make it practical, that's the hard part, especially for theorists like us. But there are many possibilities. One is to use optical ring resonators. So this is actually a cartoon of the initial experiments with exceptional points. And that corresponds to one unit cell. Now you take many unit cells, just put them after like this, and you can map it directly to our chain. And they have to be coupled in a certain way, and the technology for that exists. You just need to put the pieces together, or just in a theorist's mind. The experimentalists actually have to do this, so they might disagree. But take many of these, and then to make an odd length, at the last one, you can have only one ring resonator, while all the others have two. And this kind of model have already been implemented with electrical circuits, robotic metamaterials, and so on. They just haven't looked for sensing applications. But the signatures are all there. They should be usable. We need something to measure, though. So it's a topological phenomena, as I said, so you can think about many different ways of getting the same effect. For instance, this is something where in the large system limit you can map this one onto the original sensor that we suggested, where you have just the non-Hermitian terms are gain and loss, and then you have something which looks like spin-orbit coupling, complex hopping terms. So if you have spin-orbit coupling in a ladder and gain and loss, you can also get it. And I'm sure there are many other ways of getting it, as long as you have this winding in the Brillouin zone. The thing you need to think about is going back to the basics or the beginning of the talk. We need to be in case 3, where sort of all the Pandora's box opens. We essentially need a Hermitian part of a Hamiltonian to not be diagonalized at the same time as the anti-Hermitian part of the Hamiltonian. The interference between Hermitian and anti-Hermitian is essential. I mean, if you just let your Hamiltonians go to I times the Hamiltonians, they will have the same eigenstates, right? So that's not enough. You need interference between Hermitian and anti-Hermitian parts. So dissipation and unitary dynamics need to act together. If you use only one of them, it's not very interesting. Well, it's still extremely interesting, of course, that's most of physics as we think about it, but the really unique features you get here, you need this to not commute. In every geometry, I should say, there are counterexamples where you can get it commutes in periodic boundary conditions, but not in open and so on. So we can sum up the non-Hermitian topological sensors, and I would claim that all of these are fulfilled on the theory level. Question is still practically useful. I don't know, but I know that several experimental groups are working on things like this, but I can't tell you why or how or whatever, because that's how experimentalists think. I learned. So we'll see if it's practically useful. I don't know, but I find it interesting enough to just throw out this idea. So let me finish by some brief conclusions. There are really qualitatively new aspects of topology in non-Hermitian systems. Of course, they aren't always corresponding to non-Hermitian Hamiltonians, but these things are also reflected in Liouvilleans for open quantum systems, etc. They are there in quasi-particle systems, etc. There are intriguing prospects for applications. I should mention another thing that has been suggested to be an application of non-Hermitian topology, and that's lasers. And lasers are very clearly non-Hermitian in a sense, right? And if you can use topology to stabilize lasers, it might be a good thing. But really many, many open questions remain. This is really like opening a Pandora's box, and I think we're still scratching on the surface. There are many questions left about applications. There are many questions left about very fundamental, basic questions. You could ask me thousands of questions that I have no answer to, and possibly no one else either. But think about it, if Hermitian physics, which we know is very complicated, that's one special case of this. When you open this, it's a much larger sort of universe that opens up, and we're just scratching the surface. Thanks.
So, thank you very much, Emil. So, we open for questions.
This is more like a comment. I mean, I'm not really agreeing with your way of describing science history. I mean, the use of non-Hermitian Hamiltonians it's very old. I mean,
Yes, that's why I mentioned it.
You mentioned a lot of cases, but I mean, all these things have been used in AMO physics at least for 50 or 60 years.
Yes, I know.
You didn't say that. You said that everybody said it was like a.
I said in my
that you gave a lot of examples of things which you had losses and so, but you said that everybody said, should you really do non-Hermitian Hamiltonians? But of course people do that.
Yeah, it's this thing, that the combination of topological phases.
But this is not so strange, huh? I mean,
No,
I
it's totally
understand that it's a breakthrough that you do it, because of course you always have to treat, in all kinds of systems, you have to treat that particles or energy is leaving the system, or leaving the system.
Yeah, I totally agree. And in retrospect, most of these things are totally obvious. It's more like a sort of an effect of different communities not talking to each other.
Also your exceptional points there, that's conical intersections in molecules.
Yes. Yeah, so I mentioned this case. Maybe you even know something before Kato in the 50s or 60s. But that's the one.
Exceptional points I don't know so much about, but I mean, that I don't know if it's 50 years old, but non-Hermitian Hamiltonians is.
That's right, yeah, and conical intersections, as I understand them, those are essentially my y points and y cones. And the exceptional points are the square root.
Perhaps I can ask the question. You talked about isolating the mode. Is the problem of finding an application to find something that is interesting to measure that couples to that mode in the model?
That's the main thing, yes, if it would be practically useful, because this kind of sensitivity has already been seen essentially in experiments, just not pointed out or highlighted that that's what's there.
Thank you for the nice talk. I was wondering about this amplification by exceptional point.
Yeah.
And then this particular amplification factor that you get is like a weak value for that perturbation Hamiltonian with the pre and post selection into. So I was thinking, is there a more interesting connection to that there?
Hopefully, I don't know.
Okay, thanks.
Thanks for the nice talk. I just have a question. So if you, if you include the jump terms in the how does this change the topological phenomena you just mentioned?
Oh, that's a great question. So, Lindbladians have exceptional points. They are non-Hermitian matrices. But of course, the interpretation of them is different. So, the most naive thing you can ever do is to throw away the jump term, then you immediately get a non-Hermitian Hamiltonian, as you say. But also the full Liouville is a non-Hermitian matrix. And we showed in a recent paper that you can take, for instance, this non-Hermitian SSH chain, you take a full Lindblad, which is also an approximation, by the way. But if you start with a Lindblad, then you get a non-Hermitian Hamiltonian, which is effective at short times, but there's another non-Hermitian Hamiltonian of the same kind, but with different parameter values, that tells you everything about the time evolution at all times. So you can diagonalize that one at the same time as you diagonalize the Lindbladian. You just have to, in a non-interacting, you have to double the size of the matrices. In an interacting case, you have to square it.
I see your point. So basically, you're saying that if I'm interested in a non-time behavior, non-equilibrium state behavior, I should include the jump terms, right?
That's right. Yes, it's not going to be enough to forget about the jump term. You can do some post-selection and think about it, but then you get many different trajectories, and there's this quantum jump approach and so on. And for each of the trajectories, you can think about non-Hermitian Hamiltonians. But in general, you should think about, is there another description than the short time before there is a quantum jump? And in general, the short time evolution effective Hamiltonian will fail. And that's kind of obvious when you look at it. But still, it's a non-Hermitian matrix, so it might be another matrix that's actually interesting.
So maybe start with this one more last question is that, so if that is the case, if you just take the non-Hermitian Hamiltonians to away jump terms, and so would you think that these observables you put them on these non-Hermitian Hamiltonians will be still valid at normal times?
That depends on which system you look at. So we have this example. I even have some extra slides. Somewhere I have extra slides on kind of all of physics or something. Let me see. I can at least find you the reference here. There is a system which you can define. Okay. So this is basically what you're talking about. So this is Lindblad equation, and you can write the effective Hamiltonian, and then you throw this one, then you have an effective Hamiltonian. Okay, but that's not the most general thing you can think about. In this case, you can show, well, here is a model which we devised for studying the Lindblad equation. It's similar to our sensor, but it has some dissipators like this. It turns out that you can define different types of Hamiltonians, H effective and HS, And HS is diagonalized alongside with the fully Euclidean, but not H effective. And here is HS. It's a non-Hermitian SSH model with some parameter values. And HF, well, okay, here is HS and here is HF. It turns out that you have to interchange variables. So different aspects of the dissipation enter in them in different ways. And of course, at long times, this and this is going to have totally different time evolution. And in this case, this one is the relevant one. So it's essentially, you have this damping matrix, and the damping matrix is diagonalized alongside with HS. But it also has all of the topological features of the SSH chain.
Thanks very much.
So, thanks for a very nice talk. I have a very basic question. It's about this parity time symmetry with non-Hermitian. So what exactly the relation between these two? So if you break the PT symmetry, you get non-Hermitian or vice versa.
So this goes back a long way from, well, end of 90s, when people thought of PT symmetry as a way of getting real spectra from non-Hermitian Hamiltonian. So people wanted to change the fundamental description of quantum mechanics and just get rid of hermeticity. And then they realized that there are pseudo-hermeticities, such as PT symmetry, which gives you, in a part of the spectrum, completely real spectra, even though the Hamiltonians are non-Hermitian. Now that's just a tiny corner of sort of the non-Hermitian world. But since there was this fundamental interest, people in photonics and so on try to simulate this. So in photonics it means you have balance between gain and loss. And if you have that, you can have real spectra. But you can also have what's called as a PT transition, which is spontaneous symmetry breaking, essentially. We have a transition from real eigenvalues to complex one. But it's just a very fine-tuned, or if you want, PT symmetric part of the non-Hermitian world. Of course, in the optics experiment, you can put as much gain and loss as you want. They're not necessarily the same. So it's just a special case.
But what if in this gain and loss layer, how's the exceptional point looks like?
So if you go back to my analysis of these exceptional points, in general counting the degrees of freedom, let's see, if we go back here, it turns out if you have PT symmetry, this is vanishing. dr is orthogonal to di. So you only have this, which means that you only need one tuning parameter to hit the transition. And that's why this exceptional point in PT symmetric systems is so common, because you only need one tuning parameter, not two.
So, I guess usually you say that the speaker is around for a day or two. It's going to be around for some years, I hope. So you can find it and ask more questions. If it's not the last question, I think we again say thank you.